Hello.
I would like to welcome you to Group B7's project presentation for 2FH3 on magnetic endoscope localization.
The external coils are to be placed in a belt around the patient, and each coil will generate a magnetic field. Each coil will have a current running through it separately so that the magnetic fields do not interfere. If the current in these coils changes with respect to time, the magnetic field will lead to an induced current in the sensor coils. This induced current will generate an electromotive force, EMF, depending on its position and orientation in the field, which can then be wirelessly transmitted to an external device for processing. There are 6 external coils generating the magnetic field and 3 sensor coils in which current would be induced, resulting in 18 EMF readings that would be used to locate the sensor. The magnetic field resulting from each external coil was calculated using the Biot-Savart law. The magnetic field was calculated at the center of the sensor since the sensor coils share a common center point. The magnitude of the EMF can then be calculated by taking the dot product between B, the magnetic field vectors, and S, the surface area of the sensor coils, which are a function of its orientation. Once the matrix of EMFs is generated, optimization techniques are needed in order to find the position from the EMFs. In order to obtain our results, the built-in Matlab optimization tool was used. The optimization tool is a graphical user interface for a built-in fmin-con function, which is an optimization solver for constrained problems. The equations for calculating the EMFs are input into the optimizer parameters in the form of a Matlab function called EMF sum of differences. The function calculates the sum of differences between the EMF calculated from the actual position and from the measured position. The function is basically a measure of error. This is the Matlab code for the EMF calculator. Each external coil has different parameters. There are 6 for loops calculating the magnetic field from each coil at the sensor. Here, we calculated the EMFs at each of the 3 sensor coils. Since there are 6 external coils, we will end up with 18 EMF values. Lower and upper boundaries of the solution are specified as the position coordinates can only be within the boundary of the human body itself. For simplicity, we defined the bounded region as a cube that would represent the human torso. The origin of the coordinate system is placed so that all of the points are located in the positive octant. All the external coils have a radius of 25 centimeters, and therefore we assumed the human torso to have a diameter of 50 centimeters. Therefore, the upper and lower bounds are from 0 to 0.5 meters in each direction. While we are trying to find the XYZ coordinates of the sensor inside this system, we are also trying to find its orientation. The orientation consists of 3 normal unit vectors, all of which are perpendicular to each other. So therefore, with 2 unit normal vectors, we can find the third one using a cross product. fmin-con has 4 algorithm options: interior point, SQP, active set, and trust region reflective. The interior point and SQP algorithms were suitable for our type of problem. The first solver we experimented with was the interior point algorithm, which is the recommended Matlab default solver. It assumes that the optimization function is convex. The solver takes the derivative of the objective function to determine the search direction using Newton's method. However, we do not know if the function is exactly convex in this case, so the risk of ending up in a local minima is very likely. The second one is the sequential quadratic programming, SQP, which requires the objective function to be twice differentiable and is more often used for quadratic functions and updates it at every iteration. This method is more computationally exhaustive, but it is evidently more accurate in our experiments. The solver may stop when it reaches a limit on the number of iterations or function evaluations before it minimizes the objective to the requested tolerance. The iterative display may help in interpreting the results. In order for the solver to continue processing, the objective function has to decrease, and the constraint violation as well as the first order optimality has to decrease towards 0. We experimented with different solvers provided by the built-in fminconf function, as well as several test cases for different actual points. In real life, the initial guess would be based on an a priori knowledge of the endoscope location. That is, its initial location before the next point in time. Here, we randomized our test cases and found that the further away the initial guess is from the actual point, the less accurate the optimization will be. This is because an optimization algorithm is sensitive to initial guesses. The basic optimization algorithm is based on Newton's method. The further away the initial guess is, the more likely it will converge to a local minima rather than a global minima where the solution would lie. A far-off guess may change the curvature and direction of the next guess, bringing it further away from the convergence. When the optimization is run, we look for cases where the function value would decrease, which would correspond to an approaching minimum, and an indication that the next guess has resulted in a progress towards the accurate solution. When the guess is stuck in local minima, it is hard to make progress as the next guess might result in an increasing function value instead of a decreasing value. These are some of the examples of our successful test cases. Here, the actual point lies at point 1, point 2, and point 3 at 100,010. The start point is the initial guess value. The final result is very close to the actual point. This second example demonstrates that, in general, the closer the guess is to the actual value, the more likely to get accurate results. The third test case has a different initial point at point 1, point 3, and point 4 with the same orientation, and also demonstrates successful results. The fourth example is of using different orientation. The initial guess must be very close to the actual value in order to get close results. In conclusion, magnetic localization of an endoscope is feasible. However, more refined research is required in fine-tuning the optimization solver to produce better guesses. In real life, instead of the point being a fixed constant in an M file, there would be sensors that would read EMF values in real time, and the initial guess would be generated by another algorithm. One example of such algorithm to generate an accurate initial guess is by using artificial neural networks that can be trained to efficiently compute initial guesses for the system. Overall, this project has shown that there are practical applications of magnetic localization with optimization that can help solve practical problems in the medical field. Efficient magnetic localization will enable healthcare practitioners to extract information of an endoscope's location, which will enable better control of the equipment to improve the endoscopy procedure.